Today, we're diving into the hidden math that connects two of the absolute biggest challenges in AI right now, safety and memory.
So what on earth could possibly connect stopping an AI from breaking its rules with building a better AI memory? I mean, on the surface, these seem like total opposites, right? One is all about control and restriction, the other is about growth and expansion. Well, it turns out the answer is a single, surprisingly elegant piece of linear algebra. It's this one concept that acts like a universal key, unlocking solutions in both of these very, very different fields.
We're going to call this key the universal eraser. And I want you to think of it not as some scary formula, but as a kind of geometric scalpel, something capable of performing incredibly precise surgery inside the high-dimensional space of an AI's mind.
Okay, so to understand the scalpel, we first need to understand the spotlight. In linear algebra, you have this thing called the outer product. You see it written as UUT. All you need to know is that it takes a single concept or direction, we'll just call it U, and it creates a projector. It's basically a spotlight. Anything you shine it on will only show the parts that perfectly align with that one single direction, U. Everything else goes dark.
Now, just highlighting one thing is pretty useful, for sure. But here's where the real magic happens. What if you could do the opposite? What if you could take that spotlight and subtract it from, well, from everything else? And that brings us to this, the eraser itself. The formula is I minus U prop UT. This little thing is called an orthogonal projector, and it does exactly what we just imagined. It finds every single trace of that one direction, U, and just surgically removes it. And this is the absolutely crucial part. It leaves all other information, all the other concepts and memories completely untouched. It is precision forgetting.
So we have this powerful tool. Where can we actually use it? Well, our first case file comes straight from the world of AI safety with a technique called abliteration.
The whole goal of abliteration is pretty simple. Stop a model from giving you those annoying, canned, "I cannot fulfill this request" type of answers. To do it, researchers first have to find the exact direction inside the AI's mind that represents the whole concept of refusal. We'll call that direction R. And once they find it, you guessed it, they use our geometric scalpel to surgically remove just that one direction. And here's exactly what that looks like in practice. To get a clean set of model weights, you take the original weights, W, and you multiply them by, there it is, our eraser tool, I minus RRT. This projects all of the model's knowledge away from that refusal direction. It makes it geometrically impossible for the output to have any component of that specific concept. It just erases the idea.
Okay, so that's safety. Pretty cool. Now let's pivot to our second case file, which I promise you is going to seem completely unrelated. We're talking about building a smarter, more efficient AI memory using a technique found in linear attention.
You know, when it comes to updating an AI's memory, there are really two main ways to go about it. The first is called Hebbian learning, which you can kind of think of as a leaky bucket. And the second is called the delta rule, which, as you might guess, works a lot more like an eraser. Hebbian learning is really just simple addition. The new memory is just the old memory plus some new information. So let's say you teach it apple is red, and then later you teach it apple is green. It just piles that new fact right on top of the old one. So now, in the AI's mind, apple is this weird, blurry, confused mix of both red and green. It can't forget, so it just creates interference. It's a mess. So what's the solution? The delta rule. Now take a really close look at that formula, specifically that part in the parentheses, I minus beta kkt. Does that look familiar? It should. It's our eraser, showing up again. Before the model adds the new information, it first applies the eraser to the old memory. And this quote just perfectly captures what's happening. The delta rule uses the eraser to find the exact spot on the conceptual whiteboard that's associated with a key, like apple, and it wipes it completely clean before it writes the new value. It's targeted, controlled forgetting. And that's the key to a clean memory. So let's put them side by side, because this really shows the crucial difference. Hebbian learning is just pure addition, and the result is interference. The delta rule, on the other hand, uses projection first. It erases, and then it adds. The result is what we call orthogonality, a clean state where apple is only associated with its newest update. It can properly overwrite old information.
All right, so let's bring all of this together. Let's look at the big unifying insight here, what we can really call the geometry of forgetting.
Okay, first, let's remember our AI safety case. To get rid of an unwanted behavior, the abliteration technique uses our eraser.
I minus RR transpose to change the model's weights.
And then in our AI memory case, to cleanly update a memory, the delta rule uses the exact same tool, I minus KK transpose, to erase the old memory slot before writing in the new one.
It's the exact same geometric operation. This is the core takeaway for today. The very same mathematical scalpel that's used to erase an unwanted behavior is also used to erase an old memory to make room for a new one. Controlled forgetting is the common thread that ties them both together.
And this is way more than just a neat little math trick. It reveals something pretty profound, actually. It suggests that a lot of these high-level challenges in AI, like controlling behavior and managing memory, are at their core problems of geometry. We can literally steer and manage these incredibly complex systems by precisely adding and removing directions in their vast internal space.
Which, of course, leaves us with one final and pretty provocative question. This tool is clearly powerful. So if we have a scalpel that can surgically add or remove concepts from an AI's mind, it forces us to ask a much deeper question. What concepts, what memories, or even what behaviors should an AI be allowed to forget? That's something to think about. Thanks for tuning in.